Okay, let me share my screen. Okay. So hi everyone. Welcome to Multimodal Weekly. This is a weekly webinar series hosted by our team at 12 Apps, which is an early stage Series A startup building multimodal foundation models for video understanding AI. We've been meeting virtually every single Friday over the past 55 plus weeks. Here's some of the topics that we tend to cover on a weekly basis. We have speakers talk about latest research in multimodal AI and foundation models. We have innovative application of multimodal in different verticals. Since our company focuses a lot on video understanding, we have developers talk about like their respective videos and multimodal projects that they like to share. And oftentimes we have internal team members as well as partners to come and share tutorials and guides on how to use our platform and API. In some of the recent session, we have a wide range of like speaker persona. Actually, a lot of researchers, talking about like very diverse topic, right, ranging from video repetition coding to vision foundation models to multimodal intelligent video QA, of course, video instruction tuning, multimodal benchmarking, etc. So for today's session, we'll focus on long-form video reasoning and question answering. And fun fact, all three of the speakers today both come from the same lab at Stony Brook University under Professor Michael Ryoo, Jongwoo, Kumara, and Kanchana. So the first speaker will be Jongwoo Park. He will talk about his research paper called Too Many Frames, Not All Useful, Efficient Strategy for Long-Form Video Question Answering, also known as LVNet, if I'm correct. And the second speaker is Kumara Kahatapitiya, who's going to talk about language repository for video understanding, also known as LangRepo. And finally, we have Kanchana Ranasinghe, who will talk about his project MBU focused on multimodal video understanding. So yeah, as you can see, all the presentation are very related to what we do. So super excited to hear more about the work that they've been doing and I guess the implication and impact that it can have on video understanding research. Just a quick logistic note for the attendees, feel free to send your question on the Zoom chat. And then after each speaker finish, we'll have a short Q&A chat for them. With that, I will start sharing my screen and I will unmute Jongwoo. Yeah, you can go ahead and share your screen and get started. Awesome.
Okay. Yeah, thanks for the introduction, James. Yeah, thanks for joining today's presentation. We will be discussing efficient multimodal language models for analyzing very long-form videos. And yeah, I'm the first presenter. I will talk about too many frames, not all useful, efficient strategies for long-form video QA. And let me briefly introduce myself. So I'm studying Ph.D. at Stony Brook University, and I intern at Amazon Oz, Samsung, and Motional. And my recent research interest is very long-form video understanding through LMM and LLM. And I have experience of co-founding AI-based handwriting phone service. And also, I love dogs and passionate sports fan. Okay, so let us talk about why do we need keyframes in a very long-form video. So the video is like more than 180 seconds, and recently there are videos like ranging like 10 minutes to 20 minutes. Probably there will be even longer videos in the future. Then we know that the question will ask about probably like some scenes inside of the video, and then we need to find some keyframes to answer that question, because there are many interframes which might not very useful to answer the question, or only one or two frames are needed while you need many keyframes in the videos. So there are like enormous amount of non-important frames in a very long form video, and then it's almost impossible to process all these frames to answer the question. So it's better to have a strategy to find keyframes in a very long form video. And also later, Kumara will talk about why the lengthy input to LLM will degrade the performance. So if you select many frames, which includes interframes, but not keyframes, then you will likely have a lengthy input to LLM, and it will degrade the performance. So for these reasons, we are interested in strategies to select keyframes in a long-form video. Here's the overview of LVNet. Our proposed LVNet contains a novel hierarchical keyframe selector module, followed by LLM for answers generation. As you can see in the graph, LVNet shows SOTA 68.2% accuracy with merely 12 captions. And the other work, lifelong memory accuracy is about 26.4% when using 39 captions. And video agent is like 60%, 60.2% when using 8.4 captions. And LVNet is achieving better performance than those two models. And the higher overview architecture is that the frames and keywords go into the hierarchical keyframe selector, and then it outputs the keyframes. And these keyframes go through the VLM to generate captions. And these captions are digested by LLM to answer the given question. Here's the detailed view of LVNet. Overall strategy is we generate captions by hierarchical keyframe selector and feed them to the separate LLM to answer the question. And there are 3 stages in this hierarchical keyframe selector. The first stage is temporal scene clustering, which divides the long video into scenes, enabling per scene subsampling. Second stage is coarse keyframe detector, which selects frames best aligned with keywords relevant to the query. Third stage is fine keyframe detector, which selects frames by refining keyword alignments through a template visual prompting. One second. Sorry. So here's the first stage, temporal scene clustering. It performs a visual content-aware preliminary frame sampling, unlike traditional uniform sampling. And its objective is reduces redundancy in videos by clustering similar frames. And it allows frames to be sampled from information-rich regions. What it means is that maybe some scenes span long and some scenes span short. Then we want to select the same number of frames from the scene that span long and the scene that span short, regardless of their length, because we want to select frames from both scenes. And then as long as we select certain number of frames from that scene, then we can capture the information from that scene that have similar scene information. How can we divide the segments is we calculate the pairwise distance between frames by using the features from the ResNet, and then measure the L2 distance between the feature space, and then perform the cosine similarity between those. And we cluster frames into about 15 non-overlapping sets. So there are 15 segments. And then we sample 18 frames, uniformly sample 18 frames per segments. In the second stage, we further subsamples frames from temporal scene clustering output. And the input to this second stage, coarse keyframe detection, is the frames from the first stage and a paired texture query. And how we can align this frame with a keyword is that we first generate keywords by using the templating or the LLM by giving the question and multiple choices. And after we generate the keywords, we utilize dual encoder, which is like image encoder and text encoder. And here we use the pre-trained the contrastive language image clip, and we generate the features of the image and the text, and then measure the cosine similarity between these two features. And we we calculate the score of this cosine similarity, and then we we order them in terms of the cosine similarity. So as you can see, in the first frame and keyword, we assign, it has a high similarity score. And then as you go down to the later part, we assign the frame and keyword similarity score gets lower. So we generate 32 frame and keyword matching, and then send them to the third stage, which is fine keyframe detector. In this fine keyframe detector, we enhances frame selection by using higher level reasoning and combining multiple frames. So yeah, as I described, the input to this third stage is the keyword, the frame, and then the matched keyword, and the score of that frame and keyword. So it's feed to this third stage. And then we partition frames into groups of 8, ordered by confidence scores. So here, the highest 8 similarity scores frame and keywords assigned to the same group, and the next highest similarity frame and keywords assigned to the second group, and so on. And we make 4 groups. So these are the, and then we concatenate frames in a college style. So it's visual templating. And then we ask VLM to list only the names of like 3 images most closely related to the keywords in each group. So in each group, we spit out 3 frames, which has the closest relationship between the image and the keyword. So at the end, we will send 12 frames to the next stage, which is VLM, to generate captions. So this is the result of the experimental results of LVNet on EgoSchema dataset. So as you can see, LVNet achieves 61.1% for the full set, which is SOTA in the table. And it is higher than our comparing model, which generate the similar number of frames, video agent, by about 7%. And we are using 12 frames, and then video agent is using 8.4%. And also in here, the lifelong memory, which has 26.4% in a subset accuracy when it uses 39 frames. And we are using 12 frames and then outperform that model by a large margin. And here's the result on next QA. We achieved the state-of-the-art result 72.9%, and it's 1.6% higher than the video agent. And we are also 0.9%, just about close to the Sevilla model, which is trained in the next QA. So we are not far away from the trained models. And even this fine-tuned model, Vamus, they achieve 72.5%. And even though we are zero-shot setting, we are outperforming the Vamus as well. And here's the results on IntentQA dataset. we achieve SOTA performance 71.1%, which is 6.5% higher than zero-shot model LOVI. And then also, even though we are in zero-shot setting, we are still outperforming the fine-tuned model of Amos by 2.6%. And here's one qualitative example of our model. So these are the captions generated by LVNet. And the entire video is about, there are three main activities recorded by cameraman. One is like welding handle and using hammer to make a tool, and then using the measuring tape to measure the length of the iron bar. And these are the captions generated by LVNet, and these are the frames selected by LVNet. So LVNet correctly selects the frames which are important to answer the question. And also, when we generate caption for each frame, we found the word welding torch here, which are important to answer the question later. And in here, we also found the measuring tape, which are important to answer the question later. Here in the second frame, we couldn't find the hammer word, but since out of three main activities, we detect at least two activities, even though we slightly missed the second activity, we could answer the question correctly. So this is one open-ended response from our LVNet based on the previous example. So when we say after we using this captions, concatenate this caption, and then ask that answer the following question based on the preceding descriptions. The question is about what are the three main activities. Then in our LLM, it response is that three main activities are welding torch, and then pliers and measuring tapes. So yeah, it misses the second main activity, but it correctly detects that these welding torches and measuring tapes are the two important activities in this video. So the ground truth, which is actually the multiple choice, it has the three main activities are welding handle, hammer, and a measuring tape. And as you can see, our open-ended response is very similar to the ground truth answer, except we are missing the second activity, which is hammer. But still, we actually detect the correct keyframes, generate captions correctly, and by concatenating these correct captions, we could answer the question in open-ended fashion, which are very similar to the ground truth response. So we actually show that it is because of the good ability of the capability of hierarchical keyframe detector. And another example, by uniform sampling, can show why the LVNet selects the keyframes correctly and generate good captions. So if you uniformly sample, then these three frames are the example frames selected from the video. And I mean, even though there is a frame which might have this welding torch, this frame is not really the most important frame to detect the welding torch. Maybe this scene is slightly before the welding torch or slightly after the highlights. So in the caption, we cannot detect the welding torch. And here also, in uniform sampling, maybe it can sample the frame that includes the measuring tape, but this frame is not the most prominent frame related to the measuring tape. So the frame quality is not as good as the keyframe that we selected. So the VLM cannot generate caption, which includes the words, the measuring tape. So they miss the measuring tape and then the welding torch and this hammer as well. Yeah, they actually like detect the welding here, but not in this frame, which are similar to the frame we selected in a keyframe detector. So when we actually concatenate these captions and then feed them to the LLM and then ask LLM to generate answer to this question, they say hexos, which are not true. Well, it's not one of the three main activity. And then power tools, it's not one of the main activity. So it gets quite different from the ground truth answer, and then it leads to select the wrong option. So yeah, it shows the quality of our hierarchical keyframe selector, and then why it's important to select keyframes and then generate captions based on those keyframes. And this is the more visualized way to summarize our architecture. So yeah, if I summarize, we actually input 900 frames at the beginning, and then we cluster these frames into scenes, and then we subsample them, reducing the total to around 280 frames here. And this clustering process help us to focus on the most relevant visual content. And then we apply Coarse keyframe detector. This module further narrows down the frames by selecting just 32 keyframes. And the selection is driven by the alignment of these frames with specific keywords. And these keywords are extracted based on the possible answer and options using templating or language model. And we have three coarse keyframes. They are ordered by confidence values and grouped into 4 sets, as you can see here, with A frames in each group. And these groups then undergo visual templating. And then they actually select 3 frames, which has the most highest matching between the frame and the assigned keyword. And we are using this 12 frames to generate captions of the keyframes and then send them to LLM to answer the question. So yeah, this is the end of my talk. Yeah, thank you for your attendance. And then if you have a question, then yeah, I'm happy to answer any question.
Awesome. Yeah, thanks a lot, Jongwoo, for going over LVNet and very detailed scientific explanation of the workflow. And I think this is a great summary as well. I think the whole idea is you have like a large amount of input frames and you're able to distill it into the most important keyframe that capture the fragment information in the video, right? If you have any question for Jongwoo, feel free to just put on the Zoom chat. I want to move on to the next speaker so that we have like more, I guess, enough time, right, for them to go over their presentation as well. So let me unmute Kumara. And yeah, Jongwoo, do you mind stop sharing the screen so that Kumara can share screen?
Okay, so let me share my screen. Hopefully you can see my slides. So yeah, so thanks so much, Jongwoo, for introducing LVNet, which basically focus on the efficiency or the effectiveness of the visual modality in this long-form video VQA pipeline. So in contrast, in language repository, this talk I'll introduce the effectiveness or efficiency on the language modality side of things in the same pipeline. So my name is Kumara, and this is joint work with Kanchana, Jongwoo, and Michael. All right, so let's get into it. So we start this work with some observations from applying LLMs for long video. And in this setup, we also focus on a two-stage pipeline where we have a VLM, which takes in a visual input and converts into captions, and then an LLM stage, which converts these captions and a corresponding query to an expected answer. However, if we look at the captions that are generated by such VLMs, which generally process only a single frame or a very short temporal window, if you look at the captions they generate, we can see that they are mostly redundant, because whenever they are generating a caption, they don't have what's going on outside its temporal span, which means it doesn't know that it's generating these redundant captions. And when we have such redundant captions, we can choose to dump all of them into a very long context LLM, because we know that LLMs have very long context and they can choose to consume all these captions. But if we choose to dump all of them to a long context LLM, we see that the effectiveness of VQA drops when we have larger number of captions or longer captions. So in our experiments, we see that when we have 0.5x captions or 1x captions to 2x captions, the VQA performance drops consistently. Here we show on multiple VQA data sets with a Mistral 7B LLM, the performance consistently drops. So in this work, we try to ask the question, whether is there a way to get rid of these text redundancies and improve the context utilization of these long video LLMs. If we have a such pipeline, we can choose to generate concise descriptions and then more effectively utilize the context that we have in these LLMs. Right. So let's look at the overview of how we do this. So we choose to process short video captions generated by a captioner, and we try to create this language representation, which we call language repository, which basically creates a concise version of what's already in these captions. And we have two main operations, write operation and a read operation, where the write operation focuses on removing redundancies in the video captions, whereas the read operation focuses on generating multi-scale representations that can better answer the given query. At the same time, we choose to preserve some of the metadata that we might lose when we are writing such caption information to a language repository, which I'll discuss in a moment. So if we have such a pipeline, we show that this can achieve state-of-the-art performance with significantly smaller LLMs. For instance, we experiment with 12 billion and 7 billion scale models, and it consistently outperforms models at its scale, and it often outperforms even larger models like ChatGPT scale models. Let's look at a detailed view of our pipeline. So as I mentioned, we have two main operators, write operator and a read operator. So the write operation focuses on removing redundancies. So how we do that is by grouping redundant captions and asking an LLM to rephrase them as concise descriptions. So when we decide to make them concise descriptions, we might lose some information, such as number of occurrences that we previously had of each caption and the number of or the corresponding time steps. So we choose to keep them as additional metadata information. So once we have this kind of a language repository, we can choose to apply this writing process iteratively, where we have increasingly longer temporal windows so that we create temporally multi-scale representations. So once we have such representations, we can choose to summarize this representation so that we can answer a given query with our read operation. So let's look at each of them in a bit detail. So in our write operation, we have few components. Given a set of video captions, we first, ideally what we want to do is we want to identify which captions are redundant. So to do so, what we do is basically we split the set of captions that we have into two groups, and we embed them into a language embedding space using something like clip text encoder. And based on this embedding space, we compute the similarities between these two groups, and we choose to group the highest similar captions. So with different colors, I'm trying to represent similar captions. So when we identify some of the captions are very similar, we choose to group them together. And when we have such grouped captions, we decide to rephrase them by an LLM call. We basically ask an LLM to create a concise representation or a concise description of these grouped captions. So what we basically do is we create a template where we provide grouped captions and ask the LLM to provide or spit out a concise version of these grouped captions. So here we have to be a little bit careful because our input would be a list of grouped captions, and we only want to rephrase within each group without merging any of the groups at all. So we have some guardrails here saying that you need to return rephrase list of descriptions in the same order without additional details, without merging any of the information within these groups, so that we end up with the same number of groups after rephrasing. At the same time, as I mentioned, we choose to keep other metadata such as number of occurrences and timestamps, which might be useful in some questions. So once we have such a representation, we have our read operation, which is basically a summarization, which is also based on a template operation. It's a very simple template. You give a language repository at a given temporal scale and ask the LLM to summarize it in a given number of words. We also do question conditioning as well, because we saw that it improves the performance. Right, so once we have this kind of setup, we can apply this readily to a VQA or a downstream VQA task much more efficiently, because now we have a very concise representation compared to the original set of captions, and they are more effective as well. So if you see here, we evaluate our model on 7B and 12B scales, and in a comparable set of scales, our model significantly outperforms all the baselines, and in some cases, we can even outperform much larger models like ChatGPT-based models. So we apply this on multiple benchmarks, including EgoSchema. Here I'm showing XQA. We also show in our paper XGQA, IntentQA, and so on. And the observation is the same, that we can outperform all the models at the same scale and sometimes outperform or perform comparably with models much larger. Right, so let's look at some interesting observations. So first, obviously, we show that the information from multiple temporal scales that we generate within our repository can be beneficial. For instance, if we have just a single temporal scale versus when we have multiple temporal scales, and when we choose to read from these multiple scales, we show that the performance is consistently improving compared to a baseline. And we also show the use of our metadata. So in this case, we show that the number of occurrences can be useful in the EgoSchema setup, but not the timestamps. So this, the use of metadata depends on the type of questions that you have in each of the data sets. So if the questions focus on identifying a certain time region or when a certain event occurs, then of course the timestamp metadata can be useful. But in this setup, we see that number of occurrences is most useful, because some questions ask what's the most prominent activity that's happening in a given video. But if we choose to summarize or rephrase all of these occurrences to a single occurrence, we might lose this importance. So it helps us to preserve this metadata, which is number of occurrences. And finally, we show that the underlying problem that we wanted to address, which is the loss of effectiveness when we have longer captions, is addressed by LangRepo. For instance, the baselines drop their performance when we have larger number of captions, whereas ours preserve more stable performance for long context lengths. And also we show some qualitative examples. So here I'm showing a single temporal scale I'll describe a setting with multiple temporal scales next. But here we show a set of captions that we identified and grouped together. You see, most of them are very redundant. And when we rephrase them into a concise description in our repository entry, we see that all of them are mapped into a very concise set of descriptions. At the same time, we are preserving the timestamps and the number of occurrences. And when used together with the non-redundant captions, we can create a concise description, which is useful for VQA. So if we choose to apply this iteratively across multiple iterations, where we have increasingly longer temporal spans, then we can create multiple temporal or multi-scale temporal representations. For instance, in the first scale that I'm showing here, we identify redundant captions and rephrase them into a concise captions. But among these different chunks, we might still have some redundancies. For instance, the description that I identify in red and blue are very redundant, but they are across different chunks and they do not get rephrased. But if we choose to apply this in increasingly longer chunks, then in the next iteration, they will be grouped together and then rephrased again to remove this redundancy. So in different temporal scales, we choose to create different descriptions. For instance, this description focus on 60 seconds, whereas this description focus on 90 seconds, creating a better or more high-level information regarding the video. Right, so this is pretty much it. So what we basically do is we identify and reduce redundancies in the textual modality, still preserve some interpretable representation as a language repository, which can be used to more effectively address long-form video VQA. Right, awesome. So if you have any questions, I'll be happy to take them. Otherwise, I'll hand it over to Kanchana.
Awesome. Yeah, thanks a lot, Kumara, for going over the details of LangRepo. I also put the GitHub link on the chat as well for folks who want to dive deeper into the diagrams and a lot of the details that you have mentioned throughout your presentation. Yeah, so I think since all the talk are connected, let's just go straight into the last talk, and then maybe you can reserve a couple of minutes, last few minutes question for all the speakers. So I ask Kanchana to unmute, and yeah, you can go ahead and share your screen and talk about MVU. Oops.
Yeah, thanks for that. Hi, everyone. So this is also some joint work I did with Kumara, my advisor, and another author. And so to give a quick background, I'll be the one presenting today, and I'm a PhD candidate at Stony Brook University, and I've previously done internships at Google, Meta, and Apple with their research teams. And my key research interests include localization in vision language models and also video self-supervised learning. And fun facts, I dance ballroom during my free time, and I'm a big fan of hiking and exploring the nature. This is a picture I took from a national park in Wyoming once. And so to start off my presentation, spurious behaviors in machine learning models is a challenging issue, and it's also common knowledge that a lot of deep learning models exhibit various forms of spurious correlations that seemingly result in strong behavior, but may not necessarily be the case. To explain in more detail, the Waterbirds dataset, which is an image classification task, it has this finding that if you take an image classifier, which works very well for birds, but if you take a bird and replace its background with, let's say, a bird that's always found in the sea, you replace the background with land, the performance of that classification model goes down a lot. So which means that it was wrongly using things on the background to classify a bird when you should technically be looking at the bird to make the classification if you were going to match a human. And in my work, I'm going to have a look at how these things, similar things like this, may be affecting video understanding tasks or video understanding models, and in particular, long video understanding tasks. So the first question I want to explore is, do we really learn something video specific when we look at these video understanding tasks? And this is like the key focus in this project. And maybe a secondary exploration could be, do we really focus on something like temporally long for these long video benchmarks? Like, can you get very high performance with a fraction of frames? Like, for example, Jongwoo's work showed how just 12 frames can have sufficient information to do really well on a lot of these tasks. So, but in this work, the key focus will be on this first question. And in extending to video tasks, we start off by trying to construct some naive baselines that try to test some characteristics of these tasks. In particular, we focus on two things, which we call first, the world knowledge of LLMs. So we know that large language models contain a lot of world knowledge. They are aware about the physics of the world. They are aware about common sense. They are aware about human cultures, traditions, or like the standard way we do a lot of different tasks. And the second idea is contextual knowledge of a task. For example, if I just give you a picture of some scene, you would simply by looking at that picture, you may be able to understand what are the tasks that will happen in a location like this. Or if you see some objects, people in that single picture, you could probably answer a lot of things regarding actions, activities in that picture. And after we explore some baselines that can exploit these two things, next we try to see how we could tackle these utilize these findings to tackle long video tasks. So first, we want to see how a large language model with absolutely no visual inputs, with just a question and the candidate answers, would perform on these long video question answering benchmarks. So we explored the same benchmarks that you saw in the two previous presentations. And instead of having any visual information, we first give plainly the question. And often the question itself has information, of course, has a lot of information related to what the answer should be. And we noticed that large language models often contain extensive world knowledge, and this world knowledge alone could be sufficient to answer certain questions. For example, if it's about someone washing the dishes and the question is, what does he do after washing the dishes? Using the common sense that these language models contain, they may be able to answer the question purely by that knowledge without using any of the visual information. Next, we also want to see, in addition to this question, what if we inject just a single frame, and it would just be the center frame. In our case, we don't want to do any frame selection that would give more information than from a single frame. So our idea behind a single frame is to inject some contextual knowledge about the task. For example, over here, maybe in case the image is not clear, it's a picture of someone doing their dishes at a sink in a kitchen. So this alone also would give a lot more information, and particularly powerful VLMs that contain a language modeling element inside them can utilize a lot of this contextual knowledge to answer or perform quite well on these benchmarks. So I would quickly go into some results we get from these baselines. So the first setup we showed, which has just the LLM, which we tag as just LLM, we noticed that on two benchmarks over here, EgoSchema and IntentQA, where random performance would be 20%, purely these LLMs alone can hit almost double the random performance values. And this clearly shows that of course, any benchmark that's constrained to the constraints of the real world, aka some actions that happen in the real world, will always be governed by physics and other realistic things in the world. So while constructing benchmarks, we may not be able to avoid this, especially when evaluating models. Our key finding is that we should be aware that purely the LLM we use may give some very good performance because of the fact that that LLM has this very strong world knowledge. And our second baseline, single frame VLM, we noticed that just by giving a center frame on some of these tasks, you can actually match certain existing like state-of-the-art works from a few months back. And here our key idea is that to push the idea that just contextual knowledge paired with the world knowledge of these models can correctly answer more than half of the questions in some competitive long video question answering benchmarks. So the overall message from this initial bit of exploration is that these models contain a lot of world knowledge and contextual knowledge, and any models that utilize LLMs, VLMs are prone to having good performance that may be due to this. And the good performance we see may not necessarily be from good video understanding. Because when we talk about a video understanding model, yes, it should solve the task, but also for it to be good at a wide range of tasks, for it to be good at completely unseen kinds of tasks or very new domains, that should not just be using these spurious correlations, but it should be using the actual video information. So this brings us to our next part of this project. So how could we inject information that's very video specific into maybe our best naive baseline from the above, which would be the single frame setup? And by video specific information, well, what we mean is things that go beyond the two world knowledge and the contextual information we described earlier. And in this work, we focus on two kinds of things. The first would be global video information, basically different forms of information that go beyond a single frame. And then object-centric information, the different objects that you find across a video and how they evolve or change over the time steps of that video. And this brings us to the multimodal video understanding framework here. And by multimodal here, we actually refer to these different streams of information we can extract given a video. And we particularly focus on three different kinds of information. The first we tag as global object information, or just global information about all the objects and scene contained within a long video. And second, we speak about object spatial location. So we focus on particular objects, i.e. objects that can move around, and we extract the exact spatial locations of these objects. And finally, the motion information, how these objects move across time in a single video. And our idea is to take all of this information and feed it additionally to our single frame baseline. To give a more detailed overview, so we first have a video and we just do a naive uniform sampling of frames. And for each frame, we detect the objects of each of these frames. We match these frame objects across time. And for these two tasks, we use a traditional object detector. And here we use a traditional object tracking algorithm. And in short, this simple setup gives us locations of objects across all frames of the video and also tracklets or trajectories for each of the objects. The interesting thing is whatever detector and tracker we use, we don't take it as part specific to our method. It could be something you can always replace if you want to go to a new domain. And the rest of our method can still remain the same because our setup is entirely zero shot. And later on, we also explore alternate frame selection strategies, which we explain in detail in our paper, but I would leave it at that for now. And then we go a bit more detail into these object-centric video modalities. So we look at three different kinds of things, as I explained earlier. And we want to provide all of this information to our language model at the very end, encoding this purely in the language modality. So in short, we just take all of this information and write it, like template it as natural language and provide it to our LLM in addition to whatever information we had earlier. And revisiting how we extract it, we just use traditional vision models, object detection and tracking. And we detail this further in our paper, and this can always be replaced by alternatives. So to give a simple example, for the global object information, we just give something like consider following objects in video to answer the question, and we give a list of all the objects. And for the spatial locations, we give the XY coordinates and the area of each object, and we have a template and set up like this. And for the object motion trajectories, also it's something similar where we have a set of trajectories. So to go in detail, the global object information data that gets injected here would be something like all the objects we found across all the frames. And the spatial locations, we select like the average location of objects across the frames and give it here. And for the motion information, we individually track each of the distinct objects here across all the frames, and we represent our trajectories in a form like this. Interestingly, a lot of the modern VLMs are able to reason with coordinate representations like this, and we ensure first that the LLM or VLM we use is equipped to reason with these coordinates. And we also have a system prompt which explains the coordinate representation at the very beginning. So we don't need to like fine tune the model or anything. It's there as like a zero-shot prompting setup. And at the very end, in this work, we focus purely on multiple choice question answering setup. So we borrow this likelihood selection setup from the NLP domain, and we apply it, or we tailor it to suit video question answering setups. And this gives us both a faster and more accurate setup for selection tasks. And this allows us to do quick experimentation and evaluation, leading to slightly better results. And we have a quick explanation of it here, but I would direct anyone to our paper for a more detailed understanding of what happens behind this. And finally, moving on to our results. So we have our full framework. So these two are the earlier naive baselines I described, and our full setup improves above these baselines when we provide this existing information. And while it is competitive to some prior work, the focus of this work was purely to explore these baselines that are very naive and show that these simple baselines can get above random results, and then to see if how we can push those forward. So our numbers may not necessarily be as competitive over here. And in future work, we are hoping to try and also make the resulting framework a bit more competitive. And another interesting thing what we wanted to explore was, so all of these ideas of world knowledge and contextual knowledge, they apply to these real world question answering tasks because they often involve humans and human actions. But what happens if we apply this onto some robotics domain tasks? So there aren't a lot of robotics domain visual question answering tasks. So we take this set of data sets from this benchmark known as OpenX, and we construct our own setup. And we interestingly find out that even for some robotics tasks, so the LLM only setup with world knowledge clearly fails because world knowledge doesn't seem to apply too well to the robotics domain, because most of the time these tasks are things on tabletops and they're not really too related to common sense or traditions or anything like that. But then again, we do notice that when we bring in this single frame baseline, things improve slightly above random. But also interestingly, with our full framework, especially when we replace our vision tools with things that work a lot better in the robotics domain, we get some quite good results. And this brings me to the end of my talk. And yeah, thanks a lot for joining us today, and let us know if there's any questions.
It's great. Yeah. Thanks, Kanchana, for going over very in-depth coverage of that project as well. Let's see. So there's one quick question from Gabe on the chat. You want to answer? How was the coordinate determined? I think he's probably mentioned the coordinates in the MVU framework, right? Like the global object information.
Oh, yeah.
Those kind of things.
So in our work, we first use a BLM on like the center frame to describe the objects that are present in that frame. And then we take like all of the object names and we use OWLVIT, which is object detector, to run that object detector across 8 sample frames. And the object detector gives us the coordinates. And in terms of the actual coordinate representation, why we went from normalized 0 to 1, so some prior work I did, we had used that coordinate representation system and it worked well. So we stuck to that in this work as well.
Right.
And thanks a lot, Shang. So Shang is like the second author of this work and he just put out the object detector on the chat as well.
Oh, nice. Maybe just one quick recap. If you can give a quick recap, just kind of summarize this 3 work. If you can, like, give a very brief description, summary of like how does LVNet related to LangRepo and how does that relate to MVU? I think that'd be great.
Right. So maybe let me take that question. So in all these 3 works, we focus on how we can make these long video VQA pipelines more efficient and effective. And in Jongwoo's LVNet, we focus mainly on the visual modality and how we can effectively leverage just a few keyframes to answer questions. So he was trying to address that question. And in LangRepo, we were trying to address how to remove redundancies in the textual modality so that we can have a better text representation that is also interpretable, but also effective as well. And in Kanchana's MVU, we also talked about how we can effectively or more efficiently answer questions with respect to multiple choice question answering. At the same time, how to effectively make use of video-specific information, which might not be in pure LLMs, which already have a lot of world knowledge. So all these 3 work are, I would say, try to address different components of this whole pipeline and try to make each of them effective and more efficient.
Yeah, that makes sense. And I think Kanchana, like in one of the earlier slides, you have those 2 questions, right? Which is address the video component, and then there's address the long video component. So the focus of MVU has been mostly on the first. In order to build a framework that can handle long video understanding efficiently, what do you think could be like an additional enhancement to incorporate?
I think like particularly works like Jongwoo's, which, for example, Jongwoo's work selects the 12 frames from like a very large number of frames. So like, especially this idea of keyframe selection can help very long videos quite well, because unlike a lot of prior work, which handle only like 180 frames at most, Jongwoo's work is effectively using a much larger count of frames to select those 12 optimal frames. So I think things like keyframe selection would be very important, because the actual information we need may be on a few frames, but selecting those frames from a large, dense number of frames would be very important.
Makes sense. Great. Any other question from the audience? If not, maybe just a concluding question from my end is, these are very exciting work. What could be some of the next like upcoming topics that you guys are exploring to push the future direction for these works? You can just like give a couple of few sentences answer.
Yeah, so in my case, I'm more interested in how these generic LLMs can be applied to more specific domains. Like, for instance, Kanchana briefly touched on how effective they are on robotics videos, and yeah, how effective. We might also want to look at how effective they are on like medical videos and so on. So I'm interested in how we can tackle these domain-specific scenarios with these generic LLMs, because in most cases they do not perform really well. And more recently, Xiang also authored a new paper on robotics, which tried to address the same question, which is called Lara, which is, I encourage you to check it out as well. It's very interesting. So I'm basically interested in trying to adapt this to like domain-specific settings.
Yeah,
Awesome.
I think just to reiterate, like exactly what Kumara said, that's a direction we are all exploring. And this Lara work by Xiang, who's actually on this call, takes out some of these ideas and tries to apply it in a robotics domain, framing robot control in a question answering setup, where you have a large LLM and it can, like, when you want, like, let's say you just ask the robot, I want to move object A into, or like, I want to clean up the table. Ideally, it would do it in a question answering setup where it generates all of the actions as answers to individual questions.
Okay.
Yeah, thanks for potential directions from Kumara and Kanchana. And in my case, I'm interested in utilizing more video level model instead of image level model, because even if you select keyframes, if you use image level model, then you can feed only one frame to the model per iteration, right? So the natural next step would be, how many keyframes you select, if you can feed them to the model, all of them together, so that you can analyze the entire video with the selected frames. Then you don't have to worry about the unnatural division between the segments. And also there can be the history you can understand through the video model. So these kind of like how efficiently select frames, and then even after efficiently select frames, there are still like multiple frames. It's more than one frame. So how to feed them, how to feed as much as possible to the model, and then generate a caption that analyze the entire video is, I think, interesting next step for me.
Awesome. Yeah, that's great. And also thanks for putting the link up to Lara in the chat. I just realized that paper you guys co-author with Musa and Jongjae from Madison, right? Wisconsin.
Yeah.
Mu was actually one of the speakers a few months ago in this webinar talking about like how to curate and VIP Lava, some of the previous work that he done. So yeah, it's really cool to see that collaboration. So yeah, I think we can conclude the webinar here. I think we just passed our mark. Thanks a lot for those speakers for spending time preparing your slides and delivering your presentation. I'm sure the audience can find a lot of relevant insights on how long form video reasoning and video understanding is evolving from a research point of view. And yeah, excited to see some upcoming work to keep pushing SOTA for this research direction.
And thanks so much for having us here and giving us this platform to share our work. And yeah, keep up the good work.
Perfect. Yeah.
Thanks a lot for organizing everything, James.
Yeah, thank you.
And the recording of the webinar will be available on YouTube probably within 3 to 4 weeks. So I'll be sure to notify you guys once it's up so you can share it across social media. For the rest of the attendees, we'll be running this webinar on a weekly basis. So if you're interested in this type of session, just sign up to come back next Friday. Cheers, everyone. Bye-bye.
Thank you.
Bye.
Bye-bye.